So I'm going to go ahead and move on to the next video. So we just went through the Charles Law video and where we related our volume and our temperature. So now we're going to relate our temperature to something else. We're going to relate our temperature to our pressure. Okay, so we're going to go ahead and take a look at that in this video. So for Gay-Lussac's law, you need to know the relationship between the pressure and the temperature. Okay, and so to do that, I'm going to go, this is the last one that we're going to have in the gas law unit that we're going to have a lovely animation for. So y'all are about to not to be so fortunate, I guess. Okay, so it's at the same site. It's at preparatorychemistry.com. It's great if you want to go take a look at it. The apparatus on the right we're going to use to demonstrate the relationship between gas pressure and temperature. So we're going to monitor our temperature and see what happens to our pressure. Okay, so we've already talked about how gas pressure is created by collisions, and because gas particles are always moving and they hit the walls of the container, they collide with the walls of the container, and gas pressure is the force of these collisions divided by kind of how much space there is. Okay, so for Gay-Lussac's law, we, instead of holding pressure or temperature constant like we did in the previous two laws, we're going to hold our volume constant, and we're only going to vary our pressure and our temperature. Obviously, we're also going to be keeping our number of molecules here constant as well. Alright, so the number of gas particles is kept constant by being sure that the system has no leaks. Okay, the volume is held constant by not allowing the piston to move. Alright, so we've put some pins here on the piston, so this piston can't move up and down. So the space is going to stay the same. So the way you'll see this in word problems is it'll talk about a rigid container or a steel container or a container that has a piston that is not able to be moved. Alright, so when I increase my temperature, right, my particles are going to start moving faster, right? I'm starting to wake up. Those particles are starting to start moving a lot faster. They have a whole lot more energy to them. Alright, so that's going to increase that force per collision. Okay, we're going to have more collisions. Because of that, we're going to see an increase in gas pressure. So let me show that here. You're going to see an increase in your temperature, and you should also see an increase in your pressure as well. So my temperature here is increasing. You see my molecules are moving a lot faster, and my pressure moved from about here to about here. So my pressure increased because my increased pressure led to more energy, more average velocity in my particles. So there were more collisions and greater force per collision. This increased my total force, which increases my pressure. Okay, so this kind of right here is just a logical sequence. You know, I think it would be a good idea to kind of take a look. But this is pretty much what we just talked about. And I mean, it also is going to hold true. If I decrease my temperature, then my molecules are going to move a lot more slowly. They move a lot more slowly with a lot less energy. They're not going to hit the wall as often, the walls of my container as often, and they're also going to hit the walls with a lesser force. And because of that, my pressure would actually be decreasing. So decrease in temperature, decrease in pressure. Increase in temperature, increase in pressure. So think of it in that way, and you will be golden. Alright, let me get back here so we can see some practice problems. Okay, so for type of relationship, let me just quickly, this is also going to be direct relationship, so it's just like Charles' law. And like I told you, direct ends with a T, and Gay-Lussac's law has temperature. You know, it talks about temperature, varying temperature. So it's going to be a direct relationship, T and T, you know. Alright, so if I increase my temperature, I'm increasing my pressure. And if I'm decreasing my temperature, I'm decreasing my pressure. Okay, so that's the relationship, that direct relationship that you're going to see. And we've pretty much already talked about Gay-Lussac's law using kinetic molecular theory by using the animation that you were so fortunate to see. Alright. So what formula do you use? Okay, well, what type of relationship did I say it was again? It has temperature direct. All right, so it's a direct relationship, so it's going to be just like which other law that we've had that involved temperature? Charles' law. All right, so let's write out this formula, and like I said, it's going to look a lot like Charles' law did, except in the place of volume, I'm going to have my pressure. So it's going to be pressure 1 divided by temperature 1 equals pressure 2 divided by temperature 2. Okay, so P is my pressure, and T is my temperature. All right, so that's the formula that we're going to use, and we're going to do one practice problem. Kind of, I don't want to say obviously, because maybe it's not obvious to you, but since the formula looks exactly like Charles' law, except it's pressure instead of volume, we're going to solve these problems just like Charles' law, okay? So I'm going to use that same thought process to solve a problem that is a Gay-Lussac's law problem. Okay, a gas contained in a rigid container has a pressure of 5.0 atmospheres. First of all, it says a rigid container. All right, I see that word rigid container. I should have sirens going off in my head that if it says rigid container or it says a steel container, something that it's not going to be able to expand, it's not going to be able to shrink, then I need to think Gay-Lussac's. All right, so you want to be able to think those things there. Okay. Anyway, so that container has a pressure of 5 atmospheres, has a temperature of 300 Kelvin. What will be the gas pressure when the temperature changes to 500 Kelvin? Okay, so let's look through this. So we talked about before that the first thing that we're going to do is we're going to ask ourselves, what do I have? Okay, what do I have? Okay, so I have, first thing I see is that I have a pressure. So my first pressure is 5 atm, or 5 atmospheres. Okay, and I kind of want to see, you know, what temperature goes with this pressure. Okay, well, it says it's at a temperature of 300 Kelvin. All right, so I don't have to go searching too far to find that. I have 300 Kelvin. Okay, then it asks me what will be the gas. Sorry. All right, what will be the gas pressure when the temperature changes? Let me just see if I can just click and get out of this. I'm sorry, guys. I am a failure at life. Okay. So yeah, we had, this was our 5 atmospheres, 5.0 atmospheres. This was 300 Kelvin. All right, and it says that what will my gas pressure be? So I don't know my gas pressure. All right, I don't know my gas pressure. When my temperature changes, so my temperature, my second temperature, the changed temperature here, is 500 Kelvin. Okay, so that was what do I have? So now we're going to ask ourselves, you know, do I have any conversions? Oh, looky here, we have Christmas colors. That's kind of weird. All right, so we have any conversions, and in this case I'm going to look, well, don't really need to do anything with my, I don't know what that is right there. I think I just started to write the wrong thing there. Okay, so I don't know what that is. So I'm going to say that my pressures, atmospheres, I don't really need to change that. My temperatures are in Kelvin, so I'm good. All right, so there are no conversions. Yay! Just skip a step. Skip a step. All right, so let's move on to our next step. And what I'm going to say is let's rearrange. Okay, let's rearrange our formula. Okay, so we decided our formula is pressure 1 divided by temperature 1 equals pressure 2 divided by temperature 2. Okay, what do I want to solve for? Okay, well, I want to find my pressure 2. Okay, so if I'm looking for my pressure 2 and I'm trying to rearrange this bad boy here, okay, I want to oh, not again. All right, it's just going to stay there for a second. It's fine. So we're going to multiply it times, okay. We're going to get P by itself, since it's divided by temperature 2, I'm going to multiply both sides by temperature 2. Alright, and I am left with P1 times T2 divided by T1 equals P2. Okay, so now I know what I'm looking for. I can easily solve for P2, and I'm just going to plug in and calculate. Okay, so now I'm just going to plug in and calculate. So it's going to look something, alright, it's going to look something, so my pressure 1 is 5 atmospheres. My temperature 2 is 500 Kelvin. My temperature 1 was 300 Kelvin. Alright, sorry, I forgot you up there. Kelvin! Alright, now you're back. And it's going to be equaled out to my pressure 2. Alright, I put that in my calculator. 5 times 500 divided by 300. Alright, and I'm going to get that my pressure 2 is 8.3, and my kelvins here are going to cancel, and I'm going to be left with atmospheres. And something that I didn't really mention in the Charles Law video, and I'm not sure that I mentioned it in the Boyle's Law video, there really is a fifth step if you're a good test taker. Alright, let's think about this. Alright, we have Gay-Lussac's law. It's a direct relationship. Alright, so in my problem, I saw an increase in temperature. So if my temperature increases, what is going to happen to my pressure? 3 seconds to answer. Alright, so if my temperature increases, then my pressure should also increase. Well, my initial pressure was 5 atmospheres. My final pressure is 8.3 atmospheres. I would say that it increased. So my answer makes sense. So you can think of the fifth step as, hey, does my answer make sense? Well, yes, Mr. Neiman, your answer makes perfect sense. Alright, so that's the end of the Gay-Lussac video. The next video that I should be putting up is the combined gas law video, where we kind of cram the last 3 laws that we learned together into one wonderful little formula. And sorry for this hot mess thing up here on the top. That's my bad. I'm still kind of getting used to everything. So, good luck, everybody.